Hi, my name is Dan Rayberg, and this is for CS498 Independent Research at Colorado State University. The topic that I chose to research was a combination of parallelism as well as computational geometry. The aspect that I looked into in computational geometry is specifically collision detection, and the intention here was to see if I could devise an algorithm of collision detection that would run in a parallel environment. Now, it also ends up relying a little bit on computational physics, because we're not just solving a discrete collision problem, nor are we just determining a separation distance between two bodies. We're actually trying to solve for a time of intersection between two bodies by exploiting independent tests that could happen in parallel. I do have a video that I made about halfway through this course, which goes into a little bit more depth than this one. This is meant to be a little bit more concise. But we'll still talk about the important aspects of this project. So the focus of the collision detection we're doing is primarily based in the narrow phase, which is different than the broad phase. The broad phase is some heuristic usually performed because it's cheaper and faster before we actually go to some narrow phase detection, which can be costly, but it gives us a more accurate solution or resolution to the collision problem. The broad phase is essentially looking at a step of motion of a body and creating a conservative bounding volume for the starting location and the ending location of that body. And what we do is, if we find another body within that conservative bounding volume, then we say, okay, it's worth going and doing a narrow phase collision detection as well. In the narrow phase, what we'll do is we'll look at things such as the time of intersection to make a more accurate judgment about the collision that took place. And this is in the field of continuous collision detection as opposed to discrete collision detection. And while our frames and our motions are discrete, what this means is we're actually subdividing the motion that we observed in the frame. We didn't just say that it started and ended with nothing in between. We analyze the in-between in continuous collision detection, and that could be through checking distances or checking times of intersections. So in this case, we're subdividing our integration of time by some quantity, and typically a discretized quantity. However, continuous collision detection can take many forms, so we're not necessarily subdividing time, but subdividing the interval of time integration is a good way to picture the viewing of subdivision of the interval of frames. Now, Gjk is a prominent algorithm for continuous collision detection because it can give us some projective or perspective information in the discrete frames. Specifically, it can return the shortest distance between two bodies, and we can use that information to help judge whether or not at the narrow phase level a collision occurred. This is performed by taking the two shapes and performing the Minkowski difference between them, such that we get one reduced volume, and we can compare whether or not they're intersecting or what the shortest distance is by looking at the proximity of the origin to the reduced shape from the Minkowski difference. This is very similar to looking at separating axis theorem. If we look at separating axis theorem in one dimension, we can compare line segments to determine if they overlap. But what the Minkowski difference is doing for us is it's allowing us to actually translate our line segments on a separating axis, such that if they are truly separating, the origin would be contained within them, and we would see that this generalized case in 3 dimensions actually holds true. Now, there are other forms of GJK as well. We have a Boolean version, which is for just yes or no, is there an intersection? So that would be for discrete collision detection. And there's an enhanced version that's used for fixing some floating point error in GJK, because GJK, while it's a very simple algorithm, once you go above 2 dimensions, you have to really deal with some interesting problems with floating point error. And for instance, the implementation I have in the test environment is not going to be a foolproof GJK implementation, because I take some conservative measures in terms of saying more often than not a separation has occurred, as opposed to over-favoring an intersection. Now, using GJK for continuous collision detection, and how we're focusing on building our algorithm is based on 2 forms of its use. One is speculative contacts, which essentially looks at the broad phase collision detection, and it says, okay, if the broad phase collision was detected, we're just going to look at the configuration of the system at the frame start time, do a GJK distance check, and say that the closest points between the 2 objects is a contact point that we're going to add into a contact manifold. The contact manifold in a continuous system is built out over time, and then goes through a constraint solver for typically an impulse-based solution to the intersection problem. Alternatively, we can get more precision if we use Newton's method to bisect time in a route-finding manner. And this is useful because it can tell us whether or not a intersection actually occurred, and it can give us a more accurate contact point between the 2 bodies, whereas with speculative contacts, we might actually be taking too conservative of a guess here that an intersection occurred, and we might be getting contact points that don't actually exist in a frame. Like, we might have not actually had an intersection, and that's called ghost contacts. Or but yeah, the Newton's method will give us a time of, and it's, yeah, typically more accurate, and we're not going to deal with the same issue of ghosting. However, we do have to consider that this is an iterative method, and GJK in and of itself, while it's really fast, it is necessarily an iterative method because it uses the information from a previous iteration to go in the next most optimal direction in finding the solution being what's the shortest distance, and coincidentally also whether or not there was an intersection that occurred. But because it's iterative, we can warm start it, which means we can take the previous use of GJK and push it into the next iteration of Newton's method, and typically see a performance boost there. The implementation I have here is not actually using warm starting, so that is worth noting, because in the best case scenario with warm starting, you get constant time performance. Using these 2 cases of continuous collision detection, the big question is, can we do better? And this is one of my favorite engineering questions, because once we have a solution to a problem, it's always nice to re-examine that solution as times change, and in this case as hardware changes and parallelism is a new factor. GJK is several decades old, and while parallelism wasn't new then, we certainly have more parallel capabilities now through the use of general purpose GPUs and higher core CPUs. And they have different benefits. I've chosen to focus on CPU performance here, specifically because the combination of tasks being allowed to be disjoint, because there's large cache and good branching performance, which basically means that we can also not just have conditionals and iterations that perform well, we can have good random access lookup, whereas a GPU, we typically batch things, and what that essentially means is we want our process to be well distributed to independent segments of ALUs. In NVIDIA hardware, it's referred to as warps. And there's a local cache for that warp, and the idea is we distribute the information relevant to each ALU, like one piece of the information in the local cache to each ALU, and they work in kind of lockstep going through a problem, which can pose problems when we're doing random access lookup or when we have branching code, because that might break the lockstep. And the ideal execution on a GPU would be that a process is performed in lockstep so that all ALUs are done at the same time. They start at the same time, they work on their portion of a task, and they're finished at the same time. Focusing on CPUs here, it's not as much of a worry, but we still have to somehow segment our information so that we don't deal with too much dependent workload between tasks. And of course, notably, if the problem size gets too large, it's ideally better to put it on a GPU, but if it's less than some threshold, the CPU should do just fine. So the main task is to try to build an algorithm for this collision detection problem where all of the tasks are independent of one another. So the very simple thing to do, and the original idea, which I will call naive now because it didn't work, and so this is a change since the last update on this project, but we can take all of the vertices from some incident object and test it against all of the surfaces or faces of a reference object, specifically the motion of those vertices, to find a time of intersection of each vertex. This is an embarrassingly parallel problem. That is, it is inherently independent. You don't need to worry about the other vertices to do this, so it's good for parallelism. The naive approach before was to test it against a hyperplane for all the surfaces or faces of the reference object. And the reason that I'm calling this now naive is because I was doing it in a controlled manner and thinking about ideal situations, for instance, with a box. A box has very nice hyperplanes, very easy to test whether they're valid or invalid. But once we start to go to something like a circle or a sphere, you'll see all these tangent lines, even on the discretized variants with, a finite number of faces, but suddenly you have all of these hyperplanes going off in every direction, and it's harder to actually determine which of these are valid hyperplanes to project to. So you end up with a lot of false positives on earliest time of intersections. Again, the ideal scenario for this algorithm is that it fits the embarrassingly parallel designation, which essentially means it would work really well in a massively parallel environment. Which, again, just means that every problem can be performed independently of one another. Now, the idea here is we get information from the motion of the center of mass of a body, both linear and angular velocity, but we observe the linear motion from the frame start to the frame end of a vertex. So we are forcing an assumption here, which is a bit of a heuristic, which is the motion that does happen in a given frame is not on curves. But we can compute these velocities independently for each vertex, which is the first step of the algorithm. And then the new method, instead of hyperplane projection, is doing a ray test with the velocity from the incident point to each face on the reference object. And if this ray test is valid, then we know we've yielded a valid TOI, which will then involve finding the shortest time of such that we can reset the system to the moment that the intersection occurred to get the most accurate contact point. Now, the system I currently have implemented is not dealing with a failing case. This is the ideal scenario, which is that we are actually hitting one of these triangular surfaces And also, this means that our meshes have to be triangulated surfaces. But the failing case is a little bit more complicated. I had come up with a working solution for the failing case when I was dealing with hyperplanes, but I'll have to revise my format, and as such, this isn't included in the test scenarios. But I will go over the idea of how this could be re-implemented with ray tracing. So from our ray test, if our point lies within some range outside of the triangle, and we can test this because our ray test is actually giving us barycentric coordinates, so it's pretty easy to test where we are relative to the triangle. But if the instant point from the frame start, after being projected from its velocity with the ray test, if it lies slightly outside of this triangle, then we might actually be in a situation where we have to pay attention to the adjacent neighbors of the incident point. Notably, we might have a line-line intersection, which is the next most complicated intersection that can happen with surfaces. Now, this doesn't afflict the 2D system, and in 2D we could simplify this very easily by changing perspective. For instance, if we had our instant line that might be intersecting, we could just change perspective and project the reference point to that instant line, and to not really have to worry about this issue. But we can generalize it in the 2D case for the issues we face in the higher dimensions. So in higher dimensions, if we encounter this situation, we can use some information we already have about a given triangle. We can use its surface normal, its unit normal. We can normalize the edge that we're going to be testing, take the cross product to get an additional normalized vector, and create a new coordinate system to absorb the problem in. And what we would do is we take this coordinate system and transform every point involved. So the points on the reference edge and the current instant edge segment we'll be testing. If we transform all these points, we'll actually get a perspective that looks more like the 2D case. Specifically, we'll have collapsed each reference edge onto itself, and we can then look at the instant line to set up a linear system to solve. The linear system is pretty straightforward. If well, compared to what I had halfway through this project, I had considered conditions, the ideal condition, which is both vertices are moving at the same rate, but in fact they could be moving independently from one another, so I have to come up with a means to account for that. And the idea is to actually hold one vertex still, and then give the relative velocity to the other vertex. And the linear system we'll be solving is if that one vertex is allowed to move, we can look at that line segment as one equation, and then another line segment, which is the still vertex to the point we're concerned with intersecting, and that will be our second equation. And from this, we will generate a planar system that we can solve. Of course, it might be a little tedious to solve the planar system, but it's useful to note that because it's a planar system, we don't actually have to use any iterative method to do this. We can just apply Cramer's rule, so it's actually a pretty straightforward problem to solve. But again, this is not in the current test because I haven't figured out if this is fully appropriate for ray tracing compared to when the problem was for the hyperplane originally. Now, in my test environment, I created several header files. Some of these are more valuable than others. The meshes contain a few statically defined shapes. Threadpool is what holds the Threadpool. We have our Gjk implementation and a very limited linear algebra library. The Threadpool is the thing I'm most proud of here, and I really hope that it could come to use to anyone that might want a C++ based Threadpool, because there's a lot of tricky stuff to keep everything synchronized in this system, such that we can keep our daemon threads alive that are created and then detached from the main thread so that they can run unconstrained as fast as possible. So in our constructor, we can give a thread count, or it'll just use the hardware concurrency detected, but we're giving it a thread count of -1, the hardware concurrency, so we don't have to deal with detaching threads. There is a manual array dynamically created here, and we have to use move semantics to assign new threads to the elements of this array, and then they get detached. The thread pool works by giving a G function that exists inside the class for which the thread will exist in a while loop until we're ready to actually terminate the program. The threads will be in spin lock or asleep at a starting line, and they will wait there until the main thread or parent thread tells them they can wake up. Now the parent thread does that through the dispatch call, which assigns a task count and a function for a task that will be worked on by the threads. There is an initialization that's important in case you use this thread pool immediately. You might actually start trying to dispatch the threads before they're at the starting line, so that's important to consider. The function given to the threads just needs a mutex and a integer that's used as an index for the job they'll be working on, and this is referred to as the f function. So each thread, because we have a limited amount, takes some portion of that work, and it's a kind of conservative quantity, but it's a decent enough range where most threads will be sharing the work evenly. The parent thread will unlock the child threads, and it itself will then go into spin lock or sleep, depending on whichever you're using with the system, and that's just controlled by a macro definition, so that can be switched on the fly. Generally, the spin lock is faster, but it can keep your additional cores working at max capacity, so you might actually see degradation in performance depending on the tasks the threads are doing. The threads, as soon as they're done with their job, they'll make it to a finish line, wake up the parent, and then the parent will need to reset the threads again. So the parent will need to be woken up a second time after releasing the threads to go back to the starting line. And the way that works is through an atomic counter called complete counter. Essentially what happens is once the threads are released, they will go and do their job, and then they will be keeping track of who the last thread was using atomic operations to notify the parent. So that's how synchronization is done. An example of one of these functions we can use is kind of for the hello world of parallelism, which is taking an independent operation and testing it in parallel. And here we're doing the dot product with a 14-sized component vector. However, we still have to lock, we have to have some form of dependency and synchronization between threads by locking them to be able to add the result of our multiplication into a final result. But we can also control this with atomics and other means. We can see here in the environment we have initialized our thread pool. We waited for it to be fully created. We set up time points so that we can take iterations between serial and parallel dispatches of this dot product operation for both our 14-sized vector and for an arbitrary size vector. So we can go ahead and test this. We can see that the 14 component vector took less than 1 microsecond in serial, which is not too surprising because it's not a very complicated problem, and took about 20 microseconds in parallel. That number will fluctuate depending on how warmed up the cores are, but let's go ahead and put in a value, 1000, for our arbitrary vector size and see how it performs. You'll see printed on the screen the random values that were gathered to fill in this vector. And we can see that again the serial method took less than a microsecond and the parallel method took 245 microseconds. However, we should note that that's using a software-based mutual exclusion method, and we can actually instead change this to perform an atomic operation. However, we will lose some resolution if we do that, because hardware-based atomics typically are for integer arithmetic only. So what we'll have to do is scale up our float and then do a atomic fetch add into an atomic variable. And once we have our result and translate it back to a float, we're going to lose some of the information that was at the end of the float because we would have effectively truncated our value by some amount. But this is a good demonstration to show that software-based locking for synchronization does not necessarily perform the same way as the hardware level. So we'll go ahead and run this one, and I wasn't outputting the value before of the result, but we'll make sure to output it this time. So we'll go ahead and do 1000. Again, we can see from the 14 component one, the serial method still under a microsecond. And yeah, but we'll put in our 1000 and see how the atomic operation performed. And it performed an order of magnitude better. I mean, that's substantially better. Only 10 microseconds compared to 250. You can see the resolution loss, though, with the serial method reporting 262.573, whereas we get the 262.5, but the rest of the values are not quite the same. So this would be within some margin of error. And you might be able to arbitrarily change that precision based on the size of the atomic integers you have available on your hardware to work with. But you can see that hardware level atomics are not that expensive in a sense, and they are a better way if you can use them to synchronize operation between threads, and in particular with this threading class that I'm releasing on GitHub. I would probably advise this type of operation compared to excessive amounts with the mutex object and lock guards, but they're always a failsafe that can be used. I do want to emphasize the point of not relying on dependent tasks in these parallel dispatches, and to do that, we're going to check the performance also of just doing the factoring and not the synchronized summation of the result. And I will note that the compiler is not going to optimize this out because I've turned off optimization, so it's still going to be doing this multiplication regardless. So we should still get a number out of the parallel dispatch for its execution time. Again, we can see that the 14 component is faster than the parallel execution, although I think the hardware is warming up a bit because it's getting better at numbers as we go along. We can see with our 1000 component vector that it only took 2 microseconds to do all of those multiplications in parallel. This is quite noteworthy because if we could avoid the locking mechanism, we could potentially increase performance with what we're doing. Moreover, if the problem size were large enough, we might actually see even better performance. Instead of going from 2 microseconds to 10, it could be like 2 to, a millisecond or something. I haven't changed the names of these functions. This is the implementation of the collision algorithm for finding the time of. They're still called hyperplane, just kind of out of laziness, but they are implementing a Euler-Trombor ray tracing algorithm, which is a ray to a triangle test. And if it's a valid test, then we get a good TOI result. Now what we're doing here is we're testing 3 different shapes. We have a cube, a convex hull of Suzanne the monkey, and a sphere. And they're each different complexities, going from 8 vertices to 66 vertices and 242 vertices respectively. Now what we're passing in as the index is a vertex from the incident shape, and we're looping over the faces of the reference shape. And we're only doing a like-to-like comparison here, so cube to cube, Suzanne to Suzanne, and sphere to sphere. We also have an attempt to see if we can make this better by culling the faces, so we don't have to test all the faces, we only test the relevant faces, and then we'll have a reduced execution set there. The 8 number for the culling is based on the idea that we could use something like the axis-aligned bounding volume or an oriented bounding box from a broad phase collision detection to do a wide sweep of the relevant faces, and that way we don't have to test all the vertices independently, just to gather a subset of the whole set of faces of a reference object. The reduced method works about the same. We can go ahead and see what this process looks like. We have some GJK tests, including a bisection root finding test. The incident object is set 5 units along the x-axis away from its counterpart object, and for the time of tests, it's given a velocity that negates that displacement to begin with, so it would go back to the origin. And that will just make verifying the math here a little bit easier. We'll compare the cube time in parallel with the Suzanne time in parallel with the sphere time, but then we'll do the reduction only for Suzanne and the sphere because they're much more complicated meshes. We do have some serialized operations for the moment that could be made parallel, but for the sake of these tests, they're being done in serial, and their times are still being accounted for. So if we just go ahead and put in, something for our arbitrary vector, we can see some of our results. Using GJK, we can see that the cube is 3 units away from the other cube, which makes sense because both cubes are 2 units wide. One is at the origin, and one is 5 units from the origin, so that would be 3 units between them. We can see it took only 1 microsecond to perform that distance query. For Suzanne, which is significantly more complicated, 66 vertices, and that means about 128 triangular faces, it still took very little time to perform. Suzanne is also close to being 2 units wide, but it's a little bit more odd compared to the sphere and the cube, which are 2 units wide, so it has a less accurate distance of separation. We can see that the time ofs seem to have failed for some reason with the sphere and Suzanne. I will blame my GJK implementation again because it favors separations over intersection cases, so we probably just had too many failing cases occurring with GJK. Even so, we can see it's approximately right with the cube, getting close to 0.6. It should be 0.6, given that we're traveling 5 units back to the origin at a rate of 5. We can still see, though, that it's pretty fast. I mean, well, it might be faster with the warm start, but we can see that doing the root finding took 12 microseconds, whereas one case with the cube only took 1 microsecond. And we can see even worse with the sphere, it took 65 microseconds. Of course, it's the wrong value, so warm starting and having a different implementation of GJK for the root finding case would probably help out a little bit. And we can see, though, that while it should be 0.6 even, we don't get that, and that's just from floating point error with the root finding. We can see that testing all of the vertices against all the faces of the cube in parallel with our algorithm took 6 microseconds, which is shorter than the GJK root finding. Suzanne took 9 microseconds, which is comparable to what GJK found with root finding. However, the GJK output, again, seems to be wrong. But even still, they're very similar in terms of their performance time, so that might mean that we have a lot of wiggle room in terms of using this algorithm on a CPU for smaller sets of vertices and faces. The sphere, we can also see, was actually kind of comparable to the root finding with GJK. It took about 66 microseconds. So the sphere, again, is 242 vertices, so that means about 480 triangular faces. So in total, that's 242 times 480 operations that happen in parallel. Now, we can see when we try to do the cooling time, we don't really get much of an advantage with Suzanne. And similarly, with the cooling time and using the reduced set of faces to test against, we don't really get that much of a performance with the sphere. However, I think it's probably worth exploring more cooling options, because I think we can reduce the number of problems we actually have to test in the situation, and moreover, that's just another case where we could use parallelism to try to help optimize the time in terms of finding the faces to cool, and therefore finding the relevant faces to actually test. It is worth noting, though, that even though the results here seem to indicate that we might have an advantage between the 66 vertices of Suzanne and the 8 vertices of the cube, with Suzanne's 128 faces versus a cube's 6 faces. Even though it seems like we have some sweet spot there where we might be able to outperform a root finding GJK, and again, that's dependent on warm starting with GJK, and also whether or not we can find a better cooling operation to simplify the parallel dispatch. It is worth noting that this should be scalable for cores and threads, in that if we had more threads available, we could get through the more complicated workload faster. Of course, there's a give and take with doing this on the CPU. We might see in the future an advantage in terms of the cores we currently have just at faster clock speeds, which would still help this problem. Or what would also help would be more cores, more threads, even at the same clock speed. Though it would be worth testing this operation on a graphics card in an embarrassingly parallel environment, so that we could really see on very complicated shapes how well this could actually perform. There is something else to consider here that we haven't actually seen from the parallel algorithm. We don't actually know if it gave us the correct time of intersection, so I'll go ahead and run this again, but we'll output from the sphere its time of intersections that were reported. Also, I'll go ahead and demonstrate that if we run a much larger arbitrary vector size, let's do 10,000, we might be able to see an advantage with the parallel environment. Again, though, this is not doing any synchronized operations, but just for fun, let's go ahead and check that. And it seems to have done better. The serial method took 7 microseconds now, whereas the parallel one, going from 1,000 to 10,000 multiplications, only took 3 microseconds. So don't note this 1,000, that's hard-coded into the console output. Now, if we go through our time ofs, we can see which one is the smallest, which is the goal. We would ultimately need to parse this for the smallest somehow. And again, we're dealing with a sphere that's 2 units wide, and there's 0.6. It's 2 units wide, and the instant sphere is 5 units away, going to the reference sphere at that rate of 5. So we have in fact found an accurate time of intersection. This is worth noting because we're not dealing with as much floating point error here. We're still limited by, the numerical methods that we're employing, specifically with a finite number of values we can represent with floating point numbers, but we're no longer limiting the accuracy because of bisection root finding. If you recall, the Gjk result suggested that the cube was within intersection range at just under 0.6 of our arbitrary time units. And that's a direct result of the numerical method we employed, that is the bisection root finding. So the useful case with this method that can be performed in parallel, aside from appearing to possibly offer comparable times for GJK at moderately large sized objects, certainly not massive, but moderately sized, is that we're actually solving for the time of intersection directly by employing the fact that we can just look at the independent motions of vertices to the triangles of another object and determine which one took the least amount of time. Without using root finding, we can just solve this directly. There is more to possibly explore within this topic, so I'll leave a few notes on where this work could go in the future. Firstly, there is implementing the failing case with the line-line intersections. That certainly needs to be explored. So far, doing some maths by hand seems to verify that solving the linear system after giving a relative velocity to one of the incident vertices on an instant line seems to work, and using Cramer's method to get there so that we don't have to actually use Gaussian elimination to solve the linear system. Secondly, there is the consideration of how this could perform on a graphics card for very large data sets in comparison to what we're doing on the CPU. The CPU scenario here would probably be useful for heuristic volumes of shapes, and probably for real-time applications, because we can get adequate performance, it looks like, out of this. But moreover, with the graphics card, we are starting to see, at least we've seen with the RTX series from NVIDIA and AMD is coming out with their own hardware level solution, is hardware accelerated ray tracing, which is specialized to rays cast to triangles. In those scenarios, you're actually building a bounding volume hierarchy of triangles and then casting rays in there. But there's no reason we might not be able to utilize the acceleration for that test to perform the ideal scenario test to start with for this collision algorithm. Lastly, there is the need to explore whether or not this system can work for both soft bodies and non-convex shapes. I have no reason, at least from inductive proofs so far, to consider why this couldn't work for non-convex shapes, because we're ultimately solving all these problems in parallel, testing out the cases that are invalid based on the direction of the triangle we're hitting and the direction the vertex is traveling in. And also whether or not the rigid body case needs to be so restricted. again, have no reason to believe that we can't utilize this for soft bodies. It would just be computationally slightly more expensive because we would have to compute some new information on the fly, such as when we have the failing case, we would have to recompute the normalized edge vector, whereas if we're dealing with rigid systems, we could just pre-compute that and be stored with that particular mesh. And the only thing we would have to impose on it is possibly one quaternion transformation to ensure that it's oriented to the current orientation of an instance of that shape. I think overall in this project, I'm reasonably pleased to see success with the ray tracing case. I'm a little disappointed to see that I can't just use the simplified projection to a hyperplane for issues of complexity growing when you have more complicated shapes, but it was still very nice to see that this could work with ray tracing and that the ray tracing method isn't actually too slow. There is certainly more. I'll be ambitious about looking in the future if I have the opportunity. But otherwise, I would like to thank you for your time and mention that this will be posted on GitHub. And again, with strong emphasis on the parallel dispatch system for C++, as it is more in a ready state of being used as it is and repurposed in other test environments. Again, thank you.